Howdy. Welcome to the SmartGate Center webinar titled High Altitude Electromagnetic Pulse E3 Impacts on Large-Scale Electric Grids. I'm Andrea Kishne from the SmartGate Center. First, let me ask you to send a question in the Q&A window anytime to get it answered at the end of the presentation, or raise your hand with the hand button in the Zoom window, and I will allow you to unmute yourself and ask questions after the talk. The presenter today is Dr. Thomas Overbye, O'Donnell Foundation Chair, Free Professor at Texas A&M University and Director of the SmartGate Center. Prior to joining A&M in 2017, he was a professor at University of Urbana-Champaign, University of Illinois at Urbana-Champaign. Before starting his academic career, he was employed by Madison Gas and Electric Company. He is the original developer of PowerWorld simulator and the co-founder of PowerWorld Corporation. He has extensive experience in many aspects of electric power systems, including participating in and leading numerous large-scale electric grid studies. Moreover, he's a passionate educator and co-author a widely used power system analysis and design book. He has received numerous awards for research and teaching from University of Illinois, Urbana-Champaign, and IEEE Power and Energy Society. He is also a member of the U.S. National Academy of Engineering. Dr. Overbye, take it away.
Okay, thank you, Andrea. Before I get into the presentation, I do want to extend a special thanks to Andrea, since this is actually her last webinar. She is going to be retiring at the end of January, and we are definitely going to miss her. She has been with A&M for many years, and I have had the chance to work with her pretty much my whole time here at Texas A&M. And she has been introducing our webinars since the very first one, which I think was in May of 2020. So we're going to miss you, and thank you for all the things you've done over the years, Andrea, and we hope you enjoy your retirement.
Thank you so much. Thank you. Appreciate it.
After that, I want to get into the presentation. So the goal of this presentation is to show the potential impacts of high altitude electromagnetic pulses, what we call HEMPs, or some people call them HEMPs, how they can affect the grid, and to offer some guidance on how the impacts could be mitigated. The focus of the talk is HEMPs, which are caused by nuclear explosions at high altitudes from 30 kilometers up to hundreds of kilometers. In doing this presentation, since this is a public presentation, I'm not going to provide any commentary on the vulnerability of any actual electric grid, but I will be showing you results of the techniques that we use to assess HEMP vulnerability on some synthetic fictional grids, and then using publicly derived or public synthetic HEMP scenarios. Many people have helped with this work, different organizations that are listed there. I especially want to thank my students and postdocs and staff and colleagues here at Texas A&M for the work that they have done, and also some colleagues at PowerWorld Corporation. Everything I present is done in PowerWorld Simulator, which with some of it in version 23 and some of it in the version 24 beta. The great thing about being a professor is being able to work with lots of students and staff and other faculty. And this is a picture of some of the research group that we have here at Texas A&M. So I did just want to show all the people that are working on doing power systems research here. This isn't everybody, but it's a good chunk of them. So we really appreciate their contributions. Before getting into the talk, I did want to do quick two asides. One is that we do have short courses that we offer out at our facility on our Rellis campus in Bryan, Texas. we will be offering at least 3, probably 4 short courses this coming semester, and all of them are still open for registration. If you're interested, the details are given there. The first one is a primer on the planning and operation of large-scale electric grids. That's more focused on non-technicals who want to learn more about the grid, and the other ones are more focused on an engineering audience. The second aside is every year our students run a great conference. It's called the Texas Power and Energy Conference. They've been doing that since 2017. And the next offering of the conference will take place on February 10th and 11th. Actually, there is a opening event on Super Bowl Sunday. So February 9th, we've got an opening event, and then the conference itself kicks off on the 10th and the 11th. So if you're interested in attending, I've given the registration link there. In doing a talk about hemp impacts on the grid, it sort of has a, it's not exactly the most happy of topics to talk about, since we're looking at nuclear explosions and the effects that they could have on the grid. Before getting into that, I do want to say that I think our energy future is going to be quite bright. Part of my goal as a researcher and an educator is to help in the development of a sustainable and resilient electric infrastructure for the entire world. I think we're moving rapidly in that direction, and that's a good thing. Electric grids are in a time of rapid transitions with lots of positive developments. We're adding a lot of load to the grid. That's certainly a challenge as we try to integrate in these data centers and other big loads to the grid. Transportation is electrifying, which has challenges, but also is very exciting. Of course, we're integrating in a larger, well, I guess more renewable energy, and that's a challenge as well. But in dealing with these, we also have to look at the impact of potentially severe events and what they could do to the grid. And the focus here is on one of them, and that is electromagnetic pulses. I will say some of the motivation for this talk came from an executive order that our Texas Governor Abbott issued in November 2024 about the need to protect our critical infrastructure here in the state. And one of the topics brought up in that executive order is electromagnetic threats. So I thought, well, since we've been doing research in this area for about a decade, I should at least, bring people up to speed on some of the more recent work that we've done in that area. This is just an opening slide on interconnected electric grids. It's most of the audience here is probably going to be power engineers who know this, but if you don't, it's the parts of an electric grid. We've got generation, we've got the high voltage transmission, and then we've got the load. The HEMPs are able to impact all aspects of the electric grid. Certainly there's impacts on the transmission system, but there can also be impacts on the generation, and there can be also impacts on the load. So all this has to be considered as we're studying them and looking at mitigation strategies. Couple of germane characteristics of the electric grid before we get into the details. One is electricity cannot be economically stored. Certainly we are adding more storage, and this is becoming a little less true statement as we add more storage, but for the most part, we have to match the generation to the load plus losses. The second issue is our transmission system has, the transmission system cannot be directly controlled. We can indirectly control it by where we generate, and then to some extent, we have a few controllers like phase shifters that can adjust the flow of electricity. But for the most part, the transmission grid is only indirectly controlled. Customers have been in control of their load, and that's a challenge as we're trying to meet a varying load. And then the transmission system has limits, and we often operate it close to its limits for economic reasons. The limits of the transmission system are going to play an important role in this talk. So there is a report that the National Academies did in 2017 called Enhancing the Resilience of the Nation's Electricity System. And that report looks at some of the larger risks to the grid and talks about them and talks about potential mitigation strategies. The figure there is from the report, and it talks about things that could have dire consequences on the grid, ranging from an earthquake to physical attacks, cyber attacks, all the way out to droughts. What's interesting is in this figure, it actually does not talk about HEMPs. They are not included here, but I think, and a lot of people, I believe, think they are certainly a risk to the grid, potential risk. In looking at how to deal with these larger scale events, what we call high impact, low frequency events, there's a 4-stage resilience process that we go through. One is what you can do prior to the event, what you can do during the event, what you can do after the event, and then how do you learn from the event. Most of what we're doing here on the HEMP is, of course, prior to the event, since one of these has not happened. But in planning for what to do prior to the event, part of that plan involves what we would do during the event. And then, of course, the goal is to minimize the impact of the event. So after the event, we can restore operations as quickly as possible. Of course, hopefully one will never occur, but if one did occur, then we would observe, learn, and hopefully improve. Okay, so in approaching these events, the general category, high impact, low frequency events, what we usually are doing is not trying to replicate a specific event. Many have not occurred, and within each class, there can be great variability. For example, a physical attack, you can have attacks that range from vandalism to much more severe. So we're not going to try to necessarily replicate a particular event, and nor is it to ensure that there is no loss of service, because some of these events, there's going to be loss of service, but it's to be broadly prepared and to be able to do as much as we can prior to the event. So when I talk to my students about our work in the HILF space, I say, if one of these were to occur, let's say one were going to occur tomorrow, how do we make sure that we're as prepared as possible, recognizing that in that statement, you have to also include the cost effectiveness of those preparations. I mean, you can spend a lot of money preparing for something that may never occur. So it's always a balance in what is cost effective. And it's a challenge because you're dealing with rare events that have not occurred, and it's really hard sometimes to assess the real risk of one of these events. Okay, so focusing more on electromagnetic pulses, an electromagnetic pulse can be defined as a transient burst of electromagnetic energy, and it's going to be characterized by magnitude, frequency, footprint, and type of energy. Many different processes create electromagnetic pulses. Most of them are benign or well-known, like lightning will create an electromagnetic pulse, electric switching can, geomagnetic disturbances can. The focus here is on the ones that are caused by nuclear explosions that take place at higher altitudes and what impact they can have on the grid. There is a good amount of material, or well, maybe not a good amount, but at least there's some material out there that provide some guidance on what to do. One that is a useful document that I will be mentioning throughout this talk was put out by the U.S. Department of Energy CSER office in 2023. It's called High Altitude Electromagnetic Pulse Wave Application Guide, and it gives some details on these events and what to do about them. One issue with the HEMPs is because they are taking place higher up in the atmosphere or out in space, the more common nuclear impacts, blast, thermal, radiation, would not occur on the ground. So what we would see on the ground, or what the grid would be impacted by, people would not even necessarily perceive, since it's electromagnetic pulses that we can't sense, but certainly the grid would pick them up. Okay, when talking about HEMPs, there's different time frames of interest. So the impacts of a HEMP are divided up into 3 time frames. They're called E1, E2, and E3. E1 is very short, and it has a high electric field associated with it. The electric field associated with a E1 is in the tens of kilovolts, but its time frame is very short. It is over within a microsecond. The impact of the E1 is it can take out, damage, or destroy unshielded electronics. The second one is E2. E2 is longer, going out in microseconds into potentially milliseconds. It is similar to lightning. Electric fields of volts per meter are set up. So usually when we're talking about hemp vulnerabilities, we don't focus too much on E2. E3, which is the focus of this talk, is on a longer time scale. It's a time scale of perhaps several minutes, and it causes electric fields that are on the order of magnitude of ones that we deal with when we talk about geomagnetic disturbances. They're somewhat bigger, but they're also much shorter. So a E3 event would be over within several minutes. E1's over in less than a microsecond, but the damage it can do, of course, can last much beyond that. These HEMPs and their impacts have been known since the dawn of the nuclear age. They were theorized prior to the first explosion. Many of the wires were shielded actually during the first explosion that took place in 1945, but some data was still lost due to the EMP. Several nuclear tests have been done in the late 50s and early 60s looking at the impacts that HEMPs could have. The most famous one is something that was called Starfish Prime, and it was part of a series of tests known as Operation Fishbowl. Starfish Prime was the explosion of a 1.44 megaton nuclear weapon at an altitude of 400 kilometers over the Pacific Ocean in July in 1962. So it was a pretty big device. Its impacts could be seen in Honolulu, which was about 1,400 kilometers away. Some low Earth orbit satellites were also damaged as a result of this. So that gave us data on the impacts that these could have on the electric grid. Of course, the Soviets also did some testing in the early 60s. Nuclear tests in the atmosphere, space, and underwater were banned in 1963. So a lot of the data dates back to the early 60s. Even underground testing has been mostly banned since 1996. The impact of HEMPs on the electric grid has been an area of research for quite a while. One of the early reports that I've seen is the one I pasted the cover of there from Oak Ridge National Lab that dates to 1985, so close to 40 years old now. Actually, my first IEEE technical meeting as a new engineer working for Madison Gas and Electric is a bunch of us drove from Madison up to Fond du Lac, Wisconsin, and listened to a presentation on HEMPs in, I think, 1983. That was certainly during some of the hot days of the Cold War. And I think it was around the time that the Soviets had downed that Korean airliner, killing a whole bunch of people. So it was kind of a tense time. But it's just kind of interesting that I heard a presentation on this more than 40 years ago. Okay, so in terms of the threats that these cause to the grid, E1 would cause potentially partial loss of load and generation and potentially damage to the protection system. E2 is similar to lightning. It might cause some insulation flashover. Then E3, which is the focus here, it can either impact the grid by causing geomagnetically induced currents, what we call GICs, and those GICs can saturate the transformers, and that tends to increase the reactive power loading on the grid, resulting in what causes harmonics that cause reactive power loading to increase, and you could get a voltage collapse as a result of this. And there's also the potential for transformer heating as a result of the harmonics. Longer term, we could have a potential for a cascading grid collapse and or equipment damage. Okay, if you're interested in some of the public waveforms that we use, here are some documents that give additional, more detailed information on the waveforms that you can use to study these. The focus here is not on E1, but E1 does play a role in the sense that E1, the E1 from a HEMP could damage generators and or load, but that damage would occur in a particular footprint. The size of the footprint would depend upon the weapon that was used and its altitude at which it was detonated. The diagram on the left is from the Caesar report that shows the E field as a function of distance away from the center of the detonation point. Some people call these smile diagrams because they kind of look like a smile. The one on the right is from a Ditcher report that gives another view on the footprint over the course of over the continental U.S. Okay. So I mostly talked about this. The E1, when we look at E1, we kind of look at different devices and we make an assessment for an E1 to say how impacted would this device be, and that impact could range from nothing, disruption, but you get normal operation back, manual intervention is required, or it's destroyed. So that's the starting point for the E3 studies. The E3 impacts are caused by, as the nuclear weapon explodes, it actually perturbs the Earth magnetic field. This is similar to what is caused by a geomagnetic disturbance. And when you assess these, you look at how fast does the Earth's magnetic field change with time. And we express that in a dBdt. And usually we talk about it in terms of nanoteslas per minute. When you get a nanotesla variation in the Earth's magnetic field, it's just like you are moving a magnet around a conducting sphere, and that's going to induce a voltage. How much voltage gets induced depends upon how strong that magnetic field is and how rapidly it's changing. The fishbowl tests gave us some data on this, and this graph here, which I took from that 85 Oak Ridge report, is showing the variation in the Earth's magnetic field that was observed in terms of the B values. If you look at the slope on that curve, recognizing that what they're calling a gamma is a nanotesla, it has a dBdt much bigger than what we see in a GMD. A large GMD, like what we saw in 1859, might have a variation of 2,500 nanoteslas per minute. And you can see that that slope from 300 down to minus 700 is taking place in just a couple seconds. So that's going to give us a fast variation. The DOE application guide has some example waveforms in it. These waveforms have a time and spatially varying electric field. The graph on the left is the time variation in the maximum of the electric field. and the graph in kind of in the middle is showing the spatial footprint for that, recognizing that the highest part of the electric field is more concentrated in a particular area. The one on the right is showing values from a Ditcher report in which you start getting a high field, not at the center, not directly below where the explosion was, but kind of off to the side, sort of looking like almost a crescent moon there. So in doing these studies, we need both time variation and spatial variation. So it's a time and spatially varying electric field. What electric field gets induced from a changing magnetic field depends upon the conductance of the Earth. So as you do this analysis, you do have to know what sort of conductivity the Earth has, not just at the surface, but going down potentially hundreds of meters. There's been a lot of work in this area as a result of GMD studies. So when you do this analysis, this does have to be taken into account. Usually for the work that we do, we are assuming a time-varying electric field. So in assuming that time-varying electric field, we're getting data from someone else who has taken into account the Earth conductivity. When you have an electric field over the high voltage transmission system, it produces geomagnetically induced currents, GICs. These are produced whether you have a geomagnetic disturbance or whether you have E3 coming off of a HEMP event. And how much voltage you get, you just integrate the electric field along the line. If the electric field is directed along the line, then it's a pretty straightforward integration. Otherwise, usually we will be doing piecewise linear integration to get an assumed voltage, a DC, we call it a quasi-DC voltage since its frequency is much less than 1 hertz, much less below the electric grid frequency. Once you get these, you can then take a model of the power grid and calculate how the GICs flow everywhere in the grid. And this is something that most utilities are getting familiar with because it's done for the GMD analysis, the same sort of things that we do for representing E3 impact on the grid. Once we get the GICs, which are time varying, then you look at what sort of harmonics are going to be induced in the transformers, and this depends on the construction of the transformers. Those harmonics then increase reactive power loading, and they cause heating. This is a slide that I use in my GMD presentations, but it's pretty much the same for the HEMP. Is once you get the GICs, they're going to cause a reactive power loss in the transformer, and that reactive power loss is going to vary as the GICs vary. And during an E3 event, the GICs are going to vary pretty rapidly over the course of several minutes. So tying this all together, when we want to do a large-scale E3 impact study, what we need is a model of the power system, and that could be a real grid, or the examples here are with synthetic grids. We then also need a model of the time and spatially varying electric field caused by the HEMP event. That can be either something that is provided, by a third party, or it can be something that we just make up a synthetic grid that is based on public data, and that's what I'm showing you here. Is then we have a file format called B3D. It's binary 3D files that we use for GMD studies and for HEMP studies, and then we just kind of solve the grid using that. Because of the time scale of the HEMP, usually we will simulate these using standard stability code that also has been enhanced to model GICs. So we calculate the GICs every time step in the stability. Usually when I'm doing the stability code, we're integrating it at a quarter cycle or a half cycle. So every cycle we update the GIC values and update the reactive power loading. the transformers. When I do these presentations, people always ask if we have the ability to represent delays in the reactive power loss in a transformer with respect to the GICs, and the answer is yes. We do have those models that can represent that time delay, which would tend to be on the order of seconds. So it does play a role, but it's not the most major of roles. This is an example. This is a 2000 bus synthetic grid that Adam Birchfield made up close to a decade ago. It covers the footprint for Texas, but it's totally fictional. We built it actually using a 500, 230, 161, 115 kV transmission grid, something that we use in our classes here and use quite a bit for research. But what we're going to do is we're going to take this system, which has stability models and also has the needed GMD models, and we're going to apply a time spatially varying electric field to it. This is a snapshot in that simulation. So I take that simulation electric field, and in this figure, I'm contouring at a particular point in time. That contour there, the darker regions are indicating regions that have a higher electric field magnitude. The way the field direction is during an HEMP event is that they tend to be circulating around. So if you, I didn't put the arrows for the electric field on this display, but the yellow arrows are showing the induced geomagnetic currents in this grid, and you can kind of see that they are circulating around. That circulation is driven by this time varying HEMP event. And then as you do the simulation, you can look at what happens to the voltages, what happens to the frequency, what happens to reactive power loadings on your generators and things like that. This is an example of the voltage variation on that 2000 bus case. This image actually shows all 2000 bus voltages. And I'm simulating a HEMP event. This is a synthetic one where I just set it up to last for a total of 60 seconds. And you can see that it is causing voltage depression. And then as the HEMP event goes away, the voltages tend to recover. How much voltage depression we get depends upon the size of the HEMP event and the magnitude of the HEMP event and its footprint. When I tried to simulate the waveform that is provided in the DOE document, which goes up to 50 volts per kilometer, actually I was getting a voltage collapse, so the simulation was not finishing. Just to show that we can do this at scale, this is an 82,000 bus synthetic grid that Adam Birchfield also made up a year or two after he made up the 2,000 bus one. What we did is we took our Texas 2,000 bus grid and we had made up a 10,000 bus grid covering the western part of the US, and then a 70,000 bus grid covering the eastern part of the US. Again, totally synthetic, so none of the lines on there are real. But we tried to make it realistic, but not real. So we have a load that is similar to the US load on there, and we actually use public data on the location of the generators. So our distribution of generation is similar to what existed, at least at the time that we made up this grid, which was close to 8 years ago now. We then took the electric field magnitude that we got out of the DOE 2023 CSER document. That shows a graph of it over time. I just ran it out for 60 seconds. The DOE waveform goes up, and then it actually goes down to 0 around 48 seconds. And then it changes polarity, so the magnitude starts going up again. I then made a synthetic waveform. This is just a donut where I kind of have a low field in the middle, and then I ramp the field up on the kind of on the inner circle, and then I ramp it down. sometimes when we do these simulations, we move our donut around on the grid. Again, it's a synthetic waveform that we can use for testing, and we can do it in public presentations like this and look at the impact on the grid. For this particular synthetic grid, if I take that donut and run it in a stability simulation, we actually get non-convergence of that simulation after about 18 seconds. So keep in mind that the maximum of the field is occurring at about 24, 25 seconds. So we're at close to probably 60, 70% of max when we lose our simulation. If I drop the magnitude, if I just have it and run it at a maximum of 25 volts per kilometer, so I take the previous waveform and just keep the same geographic footprint size but reduce the magnitude, then I can get the simulation to run all the way through. The graphic there, you're seeing a lot of voltages that are unimpacted by it. That's because it is only affecting, in this case, the Midwest, and it is not really propagating to the eastern part of the grid. In our 82,000 bus case that I ran, we actually were doing a simulation where we were looking at joining the eastern and western grids together. So we actually had the 80,000 buses coupled together. We just kept Texas separate on it. So most of the grid is not impacted by this event. The concern, though, is if you get into a severe event somewhere in this example, it would be between 25 and 50 volts per kilometer peak. It could cause a cascade, and that would be the challenge in saying, okay, what would happen as a result of that cascade, and trying to model cascades. I mean, you can model a cascade using an assumed protection system, which is perfectly fine for synthetic grid, but trying to say on a real grid what would exactly happen is a challenge. This is an example of the voltage contour that we get for that max 25 volts per kilometer scenario. It's causing voltage depression in the locations where you might expect, which are right underneath the highest part of that donut waveform. And if I had set this up in a time varying way, you would see as the electric field increases, the voltages are decreasing, and then in this case, they would recover. In the 50 volt case, they would not recover. So the question is, what do we do when there is no solution? One approach is to back down the waveform. I tried it with 50, there was no solution. I backed it down to 25, there was a solution. So I could have iterated and come up with a value, in that case, maybe 35, 40 volts per kilometer, and say, this is the maximum I can solve. We also have the ability, rather than doing stability simulations, to do more approximate modeling, where we just look at the GIC values that we're getting induced in our transformers. So this image here shows the 50 volts per kilometer scenario, not solving stability. I'm not even solving power flows. I'm just running the time and spatially varying waveform and calculating the GICs on the transformers. And you can kind of see the values there. These are the per phase effective GICs that we get. To put this in context, the NERC TPL07 standard for GMD says if a value goes above 75 volts per phase in a transformer, then you have to, that's the threshold. You can see here that we are getting many transformers with values multiple times that, and some transformers have values, a couple transformers have values that are at 10 times that value. What that would do to the transformers, we're not sure. So when people talk about testing transformers with GICs, certainly you want to test at the 10, 20, 30, 40, 50 amp values, but it's also would be good to know what happens if they get 2, 3, 4, 500 amps of GIC in them. Now, compared to a GMD, I will say this is a much shorter duration event. It's over within, in this case, it's going out about 60 seconds. So what could occur during a HEMP? There might be little or no warning. In contrast to a GMD, which we could observe solar activity at least a day ahead of time. With a HEMP, we might not have any warning. Because this requires an adversary, that adversary would have some choice on the time, location, and number of events that might occur. So when the grid is subject to this event might not be arbitrary. The system state, of course, could change abruptly. These events, as I'm showing you based on the DOE guidance, are minutes, 2 minutes in duration. So it's going to change very abruptly with very little time for initial operator engineer intervention. However, your GIC monitors, if you have them, or magnetometers, would show this event. So they would rapidly, if you're in the footprint of this, you would rapidly see that something's going on. So that does leave open the possibility of some sort of automatic control, that preventative control that could be done during this event. And then when you get into the cascading stage, that you know that this has occurred, and you know that you might have to be dealing with extreme control scenario, then there is a potential for operator intervention if a cascade starts going on the order of a few minutes or longer. So how do we improve the grid's resiliency to HEMPs? Certainly all this has to be done in the context of cost effectiveness, and that's a challenge because it's a rare event. B1, you can harden components and associated communication and control, and certainly some manufacturers are doing that. There's also a better need to develop event simulators so the power community can experience the HEMP and other HLF scenarios and kind of get a feel for what they'd be dealing with. I think if power engineers see this, they might be able to come up with some effective mitigations. Certainly, you could set up alarms to determine if a HEMP has likely occurred. Those alarms could be used to trigger potential remedial action schemes. Different, like in the West, they have a remedial action scheme that I guess is a separation of the North and South. We might want to consider that in other grids as well to prevent a cascading collapse. Real-time monitoring would be important, and as I mentioned, in triggering these. I think better visualization to know what is going on with the visualizations geared towards these high impact, low frequency, severe events. That's not going to be visualizations that you'd use for normal operation. Tools to let the electric system operate, or owners and engineers simulate these events. Certainly there's a potential to block some of these GICs, and I'm not getting into the details here, but there are GIC blockers that have been deployed in some locations for geomagnetic disturbances, and they could be potentially used here. And as always, as a researcher, I do think we need to do more research in that. And I should say some of that research is ongoing. So with that, we've got a few minutes for questions.
First question asked by Glenn Jenkins: what type of whom EMP protection enclosure might protect whom electronics, such as vacuum tube, radio equipment, or modern electronic radio transceivers equipment?
Okay, so I'm not an E1 expert, and I can't answer that really effectively. But I do know when you design devices, the more metal you can get between your device and the E1, if you get like a Faraday cage, that can be helpful. You do have to look at cable runs. So if you've got a device that is isolated and you stick it in a metal cage, it's pretty connected. If you're running a device in say a plant or something, and it's got cables that are going outside of the plant, they're going to act like antennas and pick this up and bring them right in. So it depends on the type of device.
The next question is, although inactive of 2024, IEEE Standard 4 for high voltage test techniques defines standard impulse waveforms for lightning and switching impulses. Are you aware of standards or efforts to develop a standard impulse for HEMP E3 that could be used in insulation coordination studies?
Well, on E3, it's more of a system-wide event, and with E3, what is picking up the electric field are the transmission lines. So I do think as an industry, we've made great progress in modeling the grid and potentially protecting it from the time varying electric fields that are caused by GMDs, and an E3 would have some similarity to that. So a lot of the techniques that we've developed are applicable here, and we've certainly been leveraging them in our research.
And then there is a related question for E2 and E3.
Oh, for E2? E2 is similar to lightning, most people say.
Okay. Why there is a blue spot in the SMILE idea of E1 footprint, which is less severe as per the scale?
What was that?
I guess it's maybe one of your slides. Why there is a blue spot in the SMILE idea of E1 footprint, which is less severe as per the scale?
Why don't we come back to this question?
Okay. Do you include the spatially varying ground conductivity in your grid model?
The what conductivity?
Spatially varying ground conductivity in your grid model?
In our models, what we have for the substation grounding is a resistance, so that's not spatially varying. When we get an electric field waveform, which we get in a B3D file, the people that have developed those files hopefully have taken into account the fact that ground conductivity varies with frequency, so that would be included.
How can microgrids help mitigate the effects from E3?
Well, anytime if E3 affects the bulk grid, then if you have a microgrid that is able to operate asynchronously from the main grid, then your microgrid might be fine. Just like if you have a stand, an emergency generator, if that generator is not impacted by the E1, then that generator might work just fine if there were a cascading collapse of the main grid.
Have you considered the damage to HV breakers attempting to operate with high gig across them during an E3 event? Intentionally operational as part of procedures or unintentionally due to loss of load from E1 or harmonics from E3?
Can you read that question again?
Have you considered the damage to HV breakers attempting to operate with high gig across them during an E3 event? Intentionally operation as part of procedures or unintentionally due to loss of load from E1 or harmonics from E3?
I personally have not considered the impact on a breaker, and what would happen when you have a high GIC. When you operate a breaker, you're taking advantage of the fact that the AC waveform goes through zero 2 times a cycle. So if you're trying to break DC current, that could be a challenge. But as the fault's going to have a DC offset on it anyways. So the answer is I haven't considered that.
The next question takes us to Ukraine. Has Russia used local non-nuclear EMP weapons against Ukrainian generating plants? Do you think the effects on these, such local EMP on GNT would be similar to HEMP? Also, and tests on HEMP effects on PV panels? I guess that's US question too.
I have no idea what Russia has done in Ukraine beyond what I read in the press. So I have no idea what Russia is. I haven't heard anything about Russia using these devices on Ukrainian plants, so I can't comment on that. I do know people are testing different devices. I believe EPRI's got test facilities for E1. I think some of the national labs have test facilities for E1 where they can go and test different devices to look at their vulnerability to E1.
How about tests on HEMP events on PV panels?
Well, right, that would include potentially, I mean, I don't know the specifics, but I think there's some reports that talk about, public reports that talk about testing different devices to different E1 events.
What do you think? Are there any of the filters sold, such as EMP Shield, have any value for a home or car?
I am not familiar. I mean, I'm familiar with the general basis for shielding from an E1, but I can't talk about particular products there.
Can you describe what NERC's ISAC is doing with the real-time interval metering data resiliency PV simulation pilot? Does it include HEMP and so on?
Did you say with NERC?
Yes, NERC's ISAC is doing.
I don't know the particulars on what NERC is doing at the moment. NERC did have a task force looking at HEMPs, and I attended a number of those meetings, but I think that task force got disbanded. So I don't know that I don't know of anything that NERC is doing in this area right now.
Are you familiar with the GIC blocking devices developed by Primus? If so, what do you think of their effectiveness?
Well, I am familiar with the GIC blocking devices, including the ones developed by Primus, and we've done studies looking at the impact of GIC blocking devices on GMD events, and we've also looked at them on HEMPs. The gist of a GIC blocking device is because these GICs are quasi-DC, if you put a capacitor in the neutral on a transformer, that capacitor will block the DC current while still allowing the AC fault current to go through it. So they can be quite effective in blocking the GICs at a particular transformer. Why we need system level studies is when you block the GICs in one location, they're going to go to another location. So we've included that in the software that we use. We use the PowerWorld software, and it can model GIC blocking devices in them. So I believe I don't know the recent number that are deployed, but I know some have been deployed and used in practice.
You modeled the effects of geomagnetic latitude on the waveforms?
Well, when you calculate a waveform coming off of a HEMP, it does depend on the latitude, but usually, we are either using synthetic grids that we just make up, but that would not include that, or somebody else is providing us with the electric field to study that. I know from some of the documents that I referenced there, they do mention the impact of latitude. In fact, I think some of the documents that I put in the presentation show the impact of different fields at different latitudes.
What are your thoughts on the digital substation EMP mitigation module for protection against HEMP as installed by Centerpoint Energy?
I don't know the particulars of what CenterPoint Energy has installed in their substation. I think it's good that utilities are looking at this and, in the design of their substation. And I know some of the equipment manufacturers, probably a lot of the equipment manufacturers, are looking at this as well and trying to make sure that their substations are shielded from these devices or these impacts. And I should say with the E1, this talk is focused on nuclear explosions, but you can generate electromagnetic pulses with different devices. What a nuclear weapon, of course, has is just a lot more energy, but people could theoretically create a device that could impact the substation in an E1 sense if it's close enough to the substation. So shielding a substation, I think that's a good thing to do.
Have you seen the new waveform out of IEC standard increasing the E3 peak to 100 voltage per kilometer and lasting out to 1,000 seconds?
I have not seen that one, but that I did see one that I think the earlier one was 85 volts per kilometer, and I can't remember how long it lasts. If somebody comes out with different waveforms, we can certainly simulate different waveforms. If you took that DOE waveform and I showed the graphic for how long it lasted, if you increase its magnitude or increase its duration, then, assuming it's got the same spatial variation, it's going to be more of a challenge to the grid.
Are there any projects you are aware of that can detect harmonics caused by the half cycle saturation of transformers that could be used to protect downstream equipment?
Well, I know the harmonics are detectable. We're working on a DOE project with EPRI looking at GMDs, and EPRI was showing us a graphic of the harmonics caused by the storm that occurred in the geomagnetic disturbance that occurred in May when everybody saw the northern lights, and they were showing the harmonics. So yeah, harmonic devices are widespread. And certainly that data can be used to help in a GMD, and it could also be used to help in a HEMP.
Is there any public data or experience on HEMP from an experimental perspective from past nuclear weapon tests?
Well, the Oak Ridge report that came out in 1985, that had a spatial waveform in it that we used in some of our initial work. So yeah, there are waveforms that are available. The spatial variation, like the DITRA reports that I listed there, show images of the spatial variation from different devices detonating at different heights. So yeah, there's certainly images out showing the impacts.
Would you mind summarizing again what's effective against E1?
Well, again, this presentation was mostly focused on E3, but if you have an electric field that's changing with time, if you can put it in some sort of container, like a metal container that can block it, then you're going to protect the device. Again, and this is something that equipment manufacturers know to do. And as some of the questions have mentioned, it's being done in substation equipment. When you do that, you do have to be careful about, cable runs and things like that. You certainly don't want your cables, unprotected cables going outside of the plant. But if you put a cable in metal conduit, you're going to have more protection on it.
I think we got to the covered the last question. And also we are up to 4 o'clock. So thank you very much, Dr. Overbye, for this update on the HEMP E3 impacts on the power grid, and also for the active participation from all the participants. And thank you for attending, everyone.
And thank you, Andrea, for your hosting these many webinars. So I would like to thank
It was really
everybody.
interesting. I enjoyed it too. Thank you so much. And please be tuned for upcoming webinars and short courses and other events.
And if anybody has any questions, you can email me as well.
Yes. Thank you. Goodbye, everyone.
Bye.